a Salt Lake City Kafka meetup. I don't know if they actually have events though.
Okay.
So we do have events, and like I said, 3 of our last 4 meetups have been about Kafka.
We've had Confluent recommended.
Confluent with Pemdo. So welcome to and that probably reflects a little bit with the turnout. This is our 3rd Kafka topic in 4 months. So, and Joe rescheduled them all, not me. But we're glad to have Richie here from WarpStream. I met him at Data Council. Did you meet him at Data? Okay, Shad met him at Data Council, so he's pretty cool. But best part about these meetups is we record everyone and put them on YouTube, and then hundreds of people watch them within the first day. So we don't ever hit the thousands, but we get hundreds within the first day. So they watch for the live updates. I have announcements. Everybody's here. So it was Jason or Jason. We do have a Forge Slack you can join if you just go to forgeutah.tech. There is a jobs channel there if you're looking. I think somebody just posted another data engineering one in there recently. That or it was on LinkedIn. One of the 2 I saw.
Yeah, I was gonna say I see people posting.
So it's one of the better job boards because the person that posts is referring. So it's okay. Yeah. So that if I have any announcements, join Forge Slack. We have a meetup next month at Recursion. I did get a speaker. He'll be talking about data modeling. There's pizza over there if you'd like to grab some. Other announcements. Join Forge Slack, jobs. Next week we have the MLOps meetup. We will be doing lightning talks, and it will be at Weave. So it'll be great. I'll be giving a lightning talk. And yeah. Without that, we have Artie. No, not Artie. I'm going to call you Artie because your last name was
Sure.
close to that. It's Richie. Richie here. You're the CEO of WarpStream, correct?
Yeah, that's right.
I want to change to you. I don't want it to be me. I want it to be the 2 of us now. CEO of WarpStream. And yeah, I'm going to go ahead and turn the time over to you. We have a mic. If you want to take questions here, I'll make sure you get some good ones.
Cool.
So it's all you.
Cool. And I don't know, since we have a smaller group, if you guys just want to feel free to interrupt me and ask questions. Since let me see if I can figure out how to share my slides now.
It's just down at the bottom where it says present.
Yeah, cool. Let me just click that. Delete that. Okay, present. Oh, there's a slides button. Very fancy. Okay, cool. Add Google Slides. All right, I just have to go through the OAuth flow real quick, I guess.
You should be able to just do a tab too if you like. So a Chrome tab, whatever's easier.
Got it. Okay. Okay, cool. I can do Utah meetup. No, not that. There we go. Cool. Can you guys see my slides?
Yes.
Awesome. All right, I'll get started. So yeah, hey everyone. I'm Richie, co-founder and CEO of WarpStream. My talk is called Beyond Tiered Storage, Serverless Kafka with no local disks. I think really what the talk is about is how we basically rebuilt something, a Kafka compatible system from the ground up with no local state. But before I jump into that, I want to talk a little bit about tiered storage because it's kind of like always the obvious question that people have is how is this different from tiered storage? Before I explain that, I guess I want to explain what is tiered storage and why do people use it. So the main reason that tiered storage was created was just because disks in the cloud are really expensive, and sometimes people want to store a lot of data or store data for a very long time in their Kafka clusters for a variety of reasons. And if you have a workload that is storing data for 7 days or 30 days or forever, as some people do, 80-90% of your infrastructure cost for that workload could easily end up being essentially paying for either replicated SSDs or EBS volumes. As local volumes are cheaper than EBS, but the difference doesn't really matter that much. You can do double or triple replication, but at the end of the day, it still ends up being like super expensive. So, if you think about like a traditional EBS volume, GP2 is kind of like the standard one you'd use in AWS. It's 10 cents per gigabyte. If you want to have 3 copies, because you want to have RF equals 3 on your Kafka cluster, you end up paying 30 cents per gigabyte. And then if you don't want to run your Kafka cluster with 98% of its disks full, it's more like 60 cents per gigabyte, basically, that you want to store in your Kafka cluster. Whereas storing data in S3 is only 2 cents per gigabyte, right? So obviously, as much as possible, if you're storing a lot of data in the cloud, you want to get it off of EBS and into object storage. And so tiered storage helps, right? It makes things better, but it's not really enough. And so what we kind of set out to do with WarpStream was get rid of the disk entirely. And there are a couple of reasons for that. The first one is just operational burden. I don't know how many of you are running Kafka yourselves, but if you've ever operated or self-hosted Kafka cluster, you know what I'm talking about. The brokers are super stateful. They've got attached storage, which ends up making operations super complicated, right? If a node dies and has to be replaced, there's a bunch of data that has to be streamed back in, and you have to add it back into the group. If you want to scale the cluster out, you have to rebalance partitions. If you want to scale the cluster in, you have to move partitions off the nodes that you're about to get rid of. Just a bunch of like stuff that you have to do. There's tools out there, Strimzy, Cruise Control, that help with all this stuff. But it's all still kind of very complicated and easy to mess up. And in general, people usually struggle with balancing. So that's one of the things that we kind of wanted to solve by getting rid of this entirely. The other one was networking. So a thing that's really common for people to do is basically send kind of like high volume telemetry data through Kafka. So like application logs, IoT data, sensor data, kind of really anything that looks machine generated tends to be super high volume. And even if you kept the retention on your Kafka really short, you keep data in there for like 8 hours because you're copying it into your data warehouse or your data lake or Snowflake or whatever. Easily like 80% of your cost for this can end up just being copying data between availability zones. So if you're not familiar, basically every time you move a gigabyte of data between 2 availability zones in basically any cloud provider, you end up paying 2 cents per gigabyte. And so, if your producer is writing to a topic partition leader in Kafka, 2/3 of the time that topic partition leader is in the wrong availability zone. And then on top of that, that leader has to copy the data to 2 of its followers. And that's in the best case scenario where you've configured fetch from follower, where your consumers are only reading from brokers in the same zone as them, which actually also has a bunch of other problems that come with it that I won't get into. But the kind of like TLDR there is that basically writing a gigabyte of data through Kafka in an HA setup is going to cost you 5.3 cents per gigabyte. Just for networking, which is also kind of crazy when you consider that you can store all of that data for a month for only 2 cents. So both of those reasons, tiered storage is cool, but like 0 disks would be much better because it would eliminate kind of both of those problems. And so I'll talk a little bit about how that works. So this is what kind of WarpStream looks like. So instead of these Kafka brokers that you're normally familiar with, we have these things called WarpStream agents. The agents are basically completely stateless, thick proxies that sit in front of the object store. And the important thing to know about agents is that besides being completely stateless, none of them are special. So no agent in particular is responsible for any topic partition. And in fact, you can write or read data for any topic partition from any agent. And so if you kind of imagine what the flow of a request looks like, you have a producer, it has some batch of data, wants to write it to WarpStream. It's using a traditional Kafka client because it's the same protocol. And because any agent can write data for any topic partition, your producer ends up always talking to an agent in the same availability zone as them. So that kind of like 2/3 of the time where you're crossing availability zones basically doesn't happen. The producer writes that data to the agent in the same zone as it. The agent buffers the data for, like 250 milliseconds or something like that, and then flushes a file to object storage. And the other thing to keep in mind here that differs from systems like I know you said had Red Panda and Confluent here recently. So one thing that differs here from those systems is that WarpStream doesn't create files that are per topic partition. Instead, the agents create files that contain data from all of the topic partitions that they received data for in the last 250 milliseconds. And that's really important because if you've ever built a system that writes and reads a lot of data from object storage, you know that you're paying per request. And so if you make too many files, it ends up being super expensive. So everything about WarpStream's storage engine is designed to kind of minimize the number of writes and reads we do against the object store directly. And so once you flush that file that contains all the data from all the topic partitions from the last 250 milliseconds, the WarpStream agents kind of basically commit the fact that that file exists into basically a special metadata store. And then once both of those things have happened, the agents will acknowledge the produce request back to the producer application. So the application only ever receives an acknowledgement from the cluster if the data has been made durable. So it's very similar to running like a traditional Kafka cluster with ax equal all. It's actually a little bit more durable because like object storage is more durable than even triply replicated disks, but kind of the same idea. And then the inner zone, because the agents never basically talk to each other cross zone. And so instead of the agents essentially replicating data to each other across availability zones like Kafka does, we use the object storage layer as both the the storage layer and the network layer. So that's kind of like a very high level overview of the architecture. And so in terms of how that actually works, before I dive into that, I just want to talk a little bit about what we like to call like cloud unit economics. And like I said before, everything about WarpStream storage engine is designed to minimize the number of put and get operations because you're paying for those. So every S3 put, I don't know how many fractions of a cent that is, but the point there is that it looks like a small number, but they add up when you're doing them hundreds or thousands of times per second. But the thing to know is that puts are expensive. Gets are cheaper, about like 10 times cheaper, but they still cost money. And so since you're paying for every IO operation, which you normally wouldn't pay when you're using like EBS or local SSDs, you have to kind of take that into account. On the flip side, networking is free, right? You never pay for any networking between your virtual machines and object storage. So that has implications. And basically you're willing to do more networking now in your architecture if you can do less of something else. And storage is really, really cheap, right? 2 cents per gigabyte compared to basically 60 cents per gigabyte with EBS. And so that also has implications for the storage system as well. You can basically trade space amplification for reductions in other parts of the system. Okay, so the first thing you have to do if you're going to build something that looks like Kafka on top of an object store is that like you can't have per topic partition files. It's like unacceptable basically. And the reason for that is you can't allow the number of partitions in your cluster to have a linear relationship with the number of put requests that you need to make to the object store. Because as I was showing in this slide, a put request is basically the most expensive thing you can do with an object store. So we need to make that as minimal as possible. And I kind of hinted at this earlier before, but just to make it slightly more concrete, in a traditional system like Apache Kafka, you have a broker. It's the leader for various different topic partitions, and it basically has one active segment per topic partition. And as new records come in for those partitions, it just appends them to the local files on disks, right? And that makes a lot of sense for a system like Kafka that's designed to run basically on local disks. But on object storage, this would cost a ton of money. It would be basically cost prohibitive. And so what we do instead is we create these files that span many different topic partitions. So, even if you have thousands and thousands of partitions that are being written to by a single agent in a given 250 millisecond window, you're still only ever creating one file and creating one put request. Sorry, I just need to drink some water. So that works. And this is kind of what the flow of this looks like. As you produce, as I was saying before, you buffer and compress, you flush to the object store. Once you flushed, you commit to the metadata store. Only once all of that is done, you act back to the client, and everything's durable and looks just like Kafka, but with higher latency. The problem with that, though, is that once you've kind of said, okay, now any agent can write data for any topic partition, you kind of introduce a problem, right? You don't have topic partition leaders anymore. And so what happens when two agents concurrently write data for the same partition, right? So in this diagram on the left, I have two agents writing data for partition 1. One agent is writing batch X, and the other is writing batch Y, and they're both going through this whole buffer compress, flush commit, ACK thing at the same time. And so the way we resolve this with WarpStream is, so you've heard of separating storage from compute. The way we like to think of this is taking it one step further, where we separate data from metadata. And what I mean by that is if you think of a traditional Kafka cluster with a bunch of files on disk representing data for a single topic partition, the metadata of like which records come first is implicit, right? Like this record comes before this record, and you know that because that's the order they're laid out on disk. With WarpStream, this record and this record may be in two completely separate files in object storage, and there's no obvious relationship in the object store that those two files have that relationship between each other. And so the way we solve that problem is that after the agents flush the data to the object store, when they go to commit to the metadata store is the one that essentially assigns the offsets to each batch and generates the total ordering for the cluster. And so another way to think about that is that essentially the metadata store acts as like the kind of leader for the entire cluster, but because the agents handle all the raw data and the metadata store only handles the metadata, you can have essentially a single thing that processes all of the metadata for the cluster, and you don't need to have the metadata and the data processed essentially by a single node. So that works. You get ordering within your topic partitions. You get offsets back. Your data is ordered, so now it's starting to look more like Kafka. But another problem you have to deal with now is that you still need to introduce data locality for reads, right? So you have a bunch of files. So your data for a specific topic is kind of exists in multiple different files, right? And if you have a lot of agents, you may have a lot of active files. And so when consumers come in, you can't, the kind of like naive way to do this would be like, okay, every time a consumer comes in and it wants to read some batch from partition 2 in topic, foo, you just go and read that data directly from the object store. Object store reads are cheaper than writes. They're 10 times cheaper, but they're not so cheap that you can just do that, right? Because again, that would work if you had 10 partitions or 20 partitions, but as soon as you have thousands and thousands of partitions, it becomes cost prohibitive, and there's kind of no point in doing all of this in the first place. So the way we solve this is within a single availability zone, the agents form essentially a distributed file cache with each other. And so what I have right here is 3 agents, and each of these colors represents a different consumer. So the blue consumer is trying to fetch data for topic B from partition 19. The orange consumer is trying to fetch data from topic A for partition 2, and the green consumer is trying to fetch data from topic A but partition 3. And so, it just so happens in this diagram that the batches of data that all of these consumers need to read, it happen to exist in the same file in the object store. And so what we do is we assign every file in the object store has essentially an agent that's like the owner for that file in the hash ring. And so any requests to read data from that file flow through that specific agent. So in this case, all the requests are going to get routed to agent 2. And then agent 2 will essentially detect in memory, okay, I have a bunch of requests coming in. They're all near each other, basically in this file. So what I'm going to do is go and read 4 megabytes of data from this file all at once, load that into my memory in small chunks, and then I'm going to serve all of these reads out of memory. And you can imagine that, this is 3 requests, but in practice, there's hundreds or thousands of concurrent requests. And the way it's kind of hard to visualize just in your head, but the way this all shakes out is that you end up essentially for all of the life, no matter how many consumers you have and how many partitions you have, you end up making basically 1 GET request for every 4 megabytes of data that's been written in every availability zone. And if you do the math on that, and I'll show some math later on in the slide, it's just, that's like 10 times cheaper than paying for interzone networking, basically. So that works for the live agents, right? You have not live agents, the live consumers. You have a bunch of consumers. They're all kind of all reading the most recent files. You can kind of fit the last 5 to 10 seconds worth of data. More than that, you can probably fit like the last 30 seconds worth of data in memory in the live agents, and everything kind of works. but sooner or later, one of your consumers is going to fall behind, or someone's going to show up and say, hey, I'd really like to read these topics from the beginning. And you no longer have this opportunity for shared IO. So if this kind of stuff on the right here where I show shared IO, I've basically taken everything in this slide and kind of compressed it into that box. And you can see that for this one consumer, it's kind of reading a completely different disjoint set of files that contain data from like much earlier in the topic. And there's no way for it to share IO with any other consumers. And so what that would mean is that for a single consumer that needs to read a single partition, a historical partition from start to finish, it would end up having to essentially make one GET request for every file that's ever been written. And if you kind of do the math on that, that ends up being basically prohibitively expensive. You would basically never want to do that. And so the way we solve that problem is we have a background system that does compaction. And this is different than the compaction that normal Kafka does for compacted topics, although we do that too. But the purpose of this compaction is just to take, gather groups of all the little files that were written, every 250 milliseconds by the agents, and smush them together into bigger files where there's more data for a single topic partition that's co-located. So you can think of it almost exactly, not exactly, but it's very similar to like a log structured merge tree in a traditional data lake or system like Cassandra, just with like a very specific compaction strategy that's cares about the ordering of the data. But if you kind of look at what happened here, I had a pre-compaction file. It had batches of data for partition 1 and batches of data for partition 2, and those things basically get combined into larger batches in the post-compaction file. And so that's how the background compaction system works. Kafka has this other feature called compacted topics. If you're not familiar with that, what compacted topics are is in Kafka, when you write a record to a partition, you can also specify a key. And that key is used for two things. One, it controls which partition the record ends up in. That's the first thing it does. The second thing, though, is if you have compacted topics enabled, the key can be used to deduplicate. So you can kind of imagine that you're doing CDC, for example, and you're periodically, as rows change in your Postgres table, every time they change, you write out the new value of that row to Kafka, and the key would be basically the primary key in Postgres. And what compacted topics do is allow you to do that basically forever. And then Kafka makes sure that only the last version of any record for any given key is maintained. So for example, if you look at this diagram, you can see that key 1 was written once, twice, three times, right? In the pre-compaction file, key 1 was written once, 3 times with values 0, 1, and 3. But then if you look in the post-compaction file, with offset 0, 1, and 3, and with values 1, 3, and 4. But when you look in the post-compaction file, a record with key 1, there's only one record, and the value that it contains is the last value that was ever associated with key 1, which is v4. And so the purpose of compacted topics, basically in Kafka, is to prevent the log file from growing infinitely when you're writing the same kind of keys over and over again, like you might with CDC or other use cases. If you squint, this kind of lets you use Kafka as like a weird KV store. And so, tier storage and open source Apache Kafka doesn't work with compacted topics, but we were like, okay, well, we're already doing compaction internally for other reasons. How hard could this possibly be? And so the thing that's kind of tricky about compacted topics is that, depending on there's two concepts. One is called I have like a whole blog post that goes into more details about this if I'm being a little too confusing. But if you imagine a one partition, like a file or a data for a partition, and it has 1 million unique keys in that file, that will be much more difficult to deduplicate if there's 10 million keys in the key space than it would be if you have 2 keys that are duplicates that are separated by 10 million records, but the number of unique keys between them is not very large, right? And so what we want to figure out is how do we somehow detect that we have duplicate keys, even in the presence of a very high number of unique keys, and do so without making tons and tons of object storage requests. And so the algorithm that we came up with to do this is kind of like a two-phase algorithm. And it's heavily inspired by the algorithm that Kafka uses, but we had to essentially retrofit it to avoid creating avoid essentially doing tons and tons of GET requests, because when Kafka is running this algorithm, it can basically get to the end of the file and then seek back to the beginning of it. But if we did 2 GET requests for every partition that we had to process, it would be too expensive, right? Like the cardinal rule of WarpStream is like no object store operations should be linearly correlated with the number of partitions in the system. And so the way it works is we have this two-phase algorithm where we open 2 streams basically for each input file. So we pay for 2 GET requests for every file. And then we advance one of the streams to the end of the first partition. And what this stream does as it's getting through that first partition is it builds up an in-memory map for every unique key, what the last offset it saw for that key was. And so if we know in memory that for going back to this thing, what this map it would build in memory would say is that, okay, for key 1, the last offset we saw was 3. And if you know that, when you're processing the partition again with the second stream, you can consult that map periodically. And every time you see key 1, if the offset is not 3, you can just discard that record. And then as soon as you see key 1 offset 3, that's the only record for that key that you need to now output to the output partition. A little tricky to explain with just a slide in my hands, but I can share a blog post afterwards that goes into a lot more detail on this. So just to kind of give you an idea of like what interzone networking will cost if you're sending really high volumes of data through Kafka in a kind of traditional HA setup. So if you're writing a gigabyte per second of data through Kafka, which can easily happen with like a big logging workload or internal logging pipeline, you're going to end up paying $1.68 million a year in interzone networking fees. We don't eliminate interzone networking entirely, but we pretty much eliminate it. 1.68 million to 2,000, it's like dollars a year. It's like a rounding error. We do replace some of that with object storage API fees, because we do have to do this compaction and we have to make these files every 250 milliseconds. But it's not the kind of key thing here is it's not a one-to-one mapping, right? So it's kind of like, we take all the interzone networking fees and we replace them with object storage API fees that are less than 1/10 of that, just to give a sense of like the scale of how these trade-offs are made. Of course, it's not like magic, right? Like the big trade-off that WarpStream makes is that it has higher latency. So the P99 producer latency, we've worked really hard to get these as low as we can. P99 producer latency for WarpStream hovers around, like 400 milliseconds. And then end-to-end latency from a producer to consumer at the P99 will be usually just under 1.5 seconds. So big trade-off there. But if you have a workload that can tolerate, still sub-second latency, basically, then you get this kind of massive cost reduction and this massive reduction in operational burden. The other thing is kind of object storage is evolving in a lot of the major cloud providers. Azure has a low latency blob store. Amazon just introduced one. GCP is actively developing one. And so this is a graph of us testing WarpStream on Amazon's lowest latency object store tier. It's called S3 Express One Zone. And with this S3 Express One Zone tier, we can get P99 producer latency under 150 milliseconds and end-to-end latency under 400 milliseconds. Now, the problem with S3 Express One Zone is that it's, in the name, it's single zone. And so if you care about being able to be resilient to the loss of an entire availability zone, then you have to write to a quorum of 3 S3 Express One Zone buckets, which is a thing that WarpStream supports. And if you do that, WarpStream ends up being about as expensive as a traditional Kafka cluster. But the cool thing about basically having full separation of compute with storage and no data tiering is that you get this big knob, right? And so you have one architecture, one system, one technology, and you can crank the knob one way to get higher latency and much lower costs, or you can crank it another way and you can get higher costs and lower latency. And you can make that trade-off on basically a workload per workload basis. And in the future, we'll make it so you can make that trade-off on a per topic basis within the same cluster. But we don't support that yet. That's it. That's WarpStream. I know I went through a lot of stuff really quickly. So, happy to answer any questions.
Does anybody have any questions? Or should I go first?
Go for it.
Okay, I had a question. So I get that. Oh, you kept talking a lot about cost between this, that, and the other, which is great. I see that that's your like kind of proposition value. My question is, as far as like data ownership, I've worked at a lot of places where they like the data to be in their like instances and none other. So how does that work? Are you hosting the S3 and we're giving the data to you, or do you like put a layer on top of our S3? How does that
Yeah.
governance model work?
That's a great question. So the way this works actually is, and that's actually I always forget to talk about this when I'm doing the technical version of this talk, which is that one of the big things that's also kind of interesting about WarpStream architecture is there's a full split between the data plane and the control plane. And so what we do is the agents and the data plane run completely in the customer's account. So basically all the data stays in an S3 bucket that not only you control, but is also in your cloud account. And our cloud account actually has no access to your S3 bucket, and we have no access to your raw data. So if you came into my house in like the middle of the night and put a gun to my head, the only thing I could ever reveal to you is the metadata that's in our cloud control plane, which is topic names, consumer group names, and the volume flowing through the topics. But all of the raw data stays in the customer's cloud account. And that's part of the reason why making it so simple to operate and stateless is important, because it makes it feasible for us to just basically throw it into the customer's account. They set auto scaling on CPU, and no one ever has to look at the agents again.
Anyone else? Dusty has a question. Yes. I like running with the microphone. Makes me happy.
One quick thought that I had as you're describing this is you're talking about the blob storage versus traditional storage on a machine. There's a certain amount of comfort I have about knowing that storage is there and will respond to me when I request a data object or the service requests a data object. Do you ever run into any issues with the blob storage not returning a data object or returning a failure to get it because it's still indexing or something of that sort?
No, modern object stores are incredibly reliable. The latency is variable, and that's kind of one of the trade-offs you make with WarpStream. That's why the P99s are kind of higher than you would expect. But in general, hour for hour, you will have way more problems with EBS volumes than you have with object storage. When I was at Datadog, we operated a very large logging system, let's say, that used EBS volumes. And we built an in-house replacement that was completely object storage based. And we had a lot of problems with local SSDs and EBS volumes and just disks doing weird things that you just stop worrying about them when you're using an object store. Like sometimes you'll get a failure or like a timeout and you just retry, but you're never going to sit there and figure out like, why did the disk on this volume on this node suddenly stop responding, or why is every f-sync now taking 3.5 seconds, or all the kind of weird spooky things that happen to SSDs with firmware basically.
Cool.
Yeah.
I have another nerdy one. So I spent some time at a previous job messing with the S3 APIs, so the write APIs. And so if you can't answer this because it's secret sauce, feel fine. But I understand there's like a couple of ways to write to S3. One being like write the entire file versus like write individual parts of a file and then close the file. And I assume that's kind of what you were talking about with your put and get stuff. So I'm just wondering what you use to say, hey, this is the end of one file, start to the next file, while you're doing those, staged writes or streamed writes, I guess is how I tend to think of it, right?
Yeah, we use multi-part uploads, which lets you do kind of the streaming semantics.
Yeah.
And yeah, we use those for compaction because sometimes compaction will generate Like it can generate like a 32 gigabyte file because that's, for whatever reason, that's what the storage engine wants to do. And trying to stage that in memory, obviously, you need a lot of RAM to do that. So, for compaction, we basically try never to have require more than 128 megabytes of RAM per active compaction, and we run one compaction at most per core. And so the way that those work under the hood is, you basically you buffer, you pick the part size. I think we default to 64 megs for compaction. It buffers 64 megabytes, sends that to S3 and is like, here's part of the file, but not the whole file. And then you keep doing that. And then once you've uploaded all the parts, you tell it, hey, I'm done. And it kind of stitches them all together into one file. You don't actually usually have to interact with that API directly. The way it works in most programming languages is you get, you say I'd like to upload a file, and it gives you essentially something that looks like a socket, and you just write into that thing and close it when you're done. And the kind of S3 wrapper takes care of the rest. But logically, it is what you're describing, where you're uploading lots of small parts, and eventually they're sealed into one file at the end.
Cool.
Yeah. And in general, we try and do everything that we can streaming internally just to keep memory consumption low.
That makes sense. Any other Kafka experts here have a question? Is anybody really a Kafka expert? Only the people that build Kafka replacements are Kafka experts, right?
Maybe. I don't know. I feel like I think we spent a lot of time looking at it, I think, from the outside, and I don't know. I wasn't like a Kafka committer or anything before we started this, so there's probably a lot I don't know about Kafka itself.
That's true. Well, cool. We don't have any more questions. Let's give Richie a big old round of applause. Thank you, Richie.
Yeah, thanks everyone.
Thanks for reaching out and volunteering to speak. So I'm gonna
Yeah, thanks for having me.
exit the full screen and then end the stream. Okay.